So far, we have discussed the largest possible number of linearly independent vectors in a vector space. Now let's talk about a related question, and in the course of our discussion, we'll introduce some fundamental linear algebra terms that we haven't encountered so far. That question is, how few vectors can you have in a spanning set? A spanning set is a set of vectors that can express any other vector in the same vector space by a linear combination. In other words, the question is, how few vectors can you have and still find every vector in the vector space by a linear combination? So for inspiration and intuition, let's, as we always do, look towards geometric vectors. So in the plane, that number is 2. You cannot have any fewer than 2 vectors and still express the entire plane. If you only have one vector, all you can express is other vectors that lie along the same line. If you have 2 vectors and they don't lie along the same line, in other words, if they are linearly independent, then you can span the entire plane. In the 3-dimensional space, that number is 3. 2 is not enough, because with 2 vectors, you can only express other vectors in the same plane. But with 3 vectors, as long as they're linearly independent, that means don't lie in the same plane, you can express all other vectors in the space. So in the 3-dimensional space, that number is 3. So what we're learning is that when it comes to geometric vectors, the fewest number of vectors in a spanning set equals the largest number of linearly independent vectors. In the case of the plane, it was 2, and in the case of a space, it was 3. And so our common geometric experience inspires the rest of linear algebra to formulate and easily prove the following theorems: that any linearly independent set with the largest possible number of vectors is actually a spanning set. In other words, it can express any vector in the space by a linear combination. Conversely, any spanning set with the fewest number of vectors is linearly independent, and that all of those sets, regardless of how you construct them, have the same number of vectors. And that magical number is called the dimension of the space. And those sets where linear independence meets the spanning property are called bases. And a basis has the desirable property that it can express any vector in the space by a linear combination and do so uniquely. These theorems are incredibly powerful, as we will learn in the upcoming videos, and have an incredible number of applications, and they're at the core of the beauty and power of linear algebra.